Hello everybody, Chapter 1, Lesson G on inverse functions. We're getting close to the end of Chapter 1, just an FYI. We have one more lesson after this on linear regression and some predictions, and then we will test Chapter 1 parts E through H. So we're getting close. Let's talk about inverse functions today. Objectives are properties and existence of inverse functions, verifying two functions are inverses algebraically, graphing, and then finding inverses algebraically as well. So let's get started. Okay, so inverse functions, let's talk a little bit about this. F of x has an inverse function, f inverse of x. This is the symbol when in notation, function notation, this is the symbol for inverse. Okay, this is not to the -1 power, this is inverse. So f of x has an inverse function, f inverse of x, if the following is true. I'm going to skip to the second bullet here, and then I'll come back to the first. If the composition of f and f inverse is equal to x in both directions, right? So f of f inverse and f inverse of f both equal this identity function x, that is the definition of an inverse. As a result of that, the domain of f of x ends up being the range of the inverse, and the range of f of x ends up being the domain of the inverse. So in plain terms, the x values of f of x become the y values of the inverse, and the y values of f of x become the x values of the inverse. So let's take a look at, let's say, a set of points. Let's go 0, 1, 2, and let's go, I don't know, 8. No, let's not go 8. That'll be too big for this. Let's go 4, -1, and 3. Okay, so if these are the inputs and outputs for f of x, so f of 0 equals 4, f of 1 equals -1, and f of 2 equals 3, then the following would be true of the inverse. Numerically, we can see this in the table, that then f of 4 would equal 0, f of 3 would equal 2, and f of -1 would equal 1. So all that we did was we swapped the x's and the y's. So let's see what this looks like graphically. Let's graph f of x first in blue. Okay, so 0, 4. Let's go here for 0, 4. And then 1, -1. And 2, 3. Okay, so I'm going to connect that. Even though these are discrete points, I'm still going to connect that so you can see something special here. Okay, now let's plot the others. -1, 1. So this will be the inverse function, f inverse of x, and 4, 0. And 3, 2. It's kind of cool. I'd like to bring to your attention that these two images are a perfect reflection over this line, and this line is y equals x. It's not coincidental that y equals x is also what the composition ends up giving us in both ways. So it's kind of cool. I mean, there's a lot of properties going on here. If I were to connect the pre-image and image points, they would form a 90-degree angle, right? This would be a right angle at each of these spots. And the distance from the green line to each of the blue and red points would be equidistant as well. So kind of cool, a lot of symmetry going on there, but some properties of the inverse function. Let's move on to the existence of the inverse function. Okay, so I was mistaken. We're going to verify that two functions are inverses here real quick. So what I want to do is in order to verify this, if g of x is the inverse of f of x, I want to show that the following is true, that f of g of x equals x and g of f of x equals x. So let's go ahead and do that. So f of g of x is equal to f of x with g of x inserted. Okay, so that would be this. Now notice that in order, these inverse operations will reduce. So the cube and the cube root will reduce. That'll give me 2 times the quantity x plus 1 over 2 minus 1. You can see where this is going. The 2's reduce, giving me x plus 1 minus 1. And the 1 and negative 1 will reduce, giving me x. Therefore, f of g of x is x. Now, that's not sufficient to say that they're inverses until I go the other direction as well. So let's input f of x into g of x. So let's write a shell of g of x, leaving space for f of x inside of it. Okay, and let's again reduce based on the operations in order. So we're going to use that order of operations, and it looks like the first thing that will happen is the 1 and negative 1 will reduce. So I will have the cube root of 2x cubed over 2. At this point you could do, well, I can't do either. I'm going to reduce the 2's. And so then I'd get the cube root of x cubed. And then finally, taking the cube root of x cubed, I get x. Okay, so we've shown that f of g of x equals x and g of f of x equals x. Therefore, f of x and g of x are inverses. Are inverses of each other. Okay, cool. So example 2, let's sketch the inverse function for the following. Let's look at a couple of properties along the way and then list some ordered pairs. So let's do that first. I'm going to go with this point 1, 0, this point 2, 1, and what looks to be that point 4, 2. Okay, I'm going to plot the inverse using those points. So I'm going to plot the point 0, 1, and then the point 1, 2, and then the point 2, 4. Now, one thing to notice is that this function, the first function, let's call it, I don't know, f of x, it has a vertical asymptote at x equals 0. Now, what have we done so far with all of the x values when we transfer that onto the inverse? We transfer the x values to y values. Therefore, the inverse will not have a vertical asymptote, it will have a horizontal asymptote at y equals 0. You can see the transfer from an x to a y here. Okay, so the graph of the inverse of f of x should look a little bit, provided I can sketch it okay, like that. And it's pretty much confirmed, right? We said that visually the two functions should be a perfect reflection over the line y equals x. It looks to match pretty well. Okay, outstanding. Let's look at the existence or the necessary characteristics for the existence of an inverse function. So the existence of an inverse function is based on a function that has an inverse if and only if it is 1 to 1. What it means to be 1 to 1 is a function that has, for every input, there is only one and one unique output. So, for example, here are a couple of 1-to-1 functions. This is 1 to 1. And so is the second one. The third and the fourth are not. Those third and fourth functions are not 1-to-1 functions. And the reason why is because, for example, this red line here, you can see horizontally, confirms that both f of -1 and f of 1 are the same output. We don't want that to be the case. So what we do is we use this thing called the horizontal line test you can see below. If you take a horizontal line and you put it through the function, that function's inverse will also be a function, right? So you can imagine the inverse of this third one would look kind of like this. However, right, where this portion of the graph maps to that portion of the inverse, and this portion of the graph to the left of 0 would map to that part of the inverse. Now, the horizontal line test, if it passes, tells us that the inverse will be a function. If the horizontal line test fails, then the inverse of the original will not be a function. So let's see if each of the inverses passes the vertical line test. The first two should. So we already sketched this one for the first one here. That's not perfect, but that would pass the vertical line test anywhere that you would be on its domain. Likewise on the second one, right? Passes the vertical line test because the original passes the horizontal line test. We saw in the third one that it would fail the vertical line test. Okay, that would fail the vertical line test. And the fourth one, this would be an interesting one to sketch. I think I might try to do it. This point looks like 2, 1, so 1, 2. This point is 1, 0, so 0, 1. This point is 0, negative 1, so that'd be negative 1, 0. This point is out there, let's say negative 1, 3, negative 1.2, comma 3. So 3, comma negative 1.2. Right around here. Ooh, that's interesting. Okay, so let's try to sketch this. Looks like it'll do something like this. Wow, that's cool. But clearly, right, that's a nice reflection over y equals x. But clearly I can draw a vertical line and it would violate there and there and there the vertical line test. Okay, so the horizontal line test, like we said below, if a function f of x passes the horizontal line test, then its inverse, f inverse of x, will pass the vertical line test. Therefore, the inverse will be a function. Okay, let's move on to some algebra using this. Okay, so let's say you're given a function, f of x, g of x, or h of x, and you want to find its inverse. You don't know what it is, and you're not trying to verify that two functions are inverses, but you want to find its inverse. You want to do three things. In the equation, replace f of x with y. So let's go ahead and start on the first one here. So step 1, I'm going to be deliberate about this. You don't have to be deliberate and say this is step 1, step 2, step 3. I'm just trying to take you through it in a manner that would be understandable. Okay, so I've got this. Step 1, check. Step 2, I'm going to interchange x and y, because with inverses, the domain becomes the range becomes the domain. Okay, so the domain of the original becomes the range of the inverse, and therefore that's why I'm going to swap x and y. So I'm just going to rearrange. I'm keeping the function the same. I'm just switching x and y in the process. Now I'm going to solve, and also step 2. This is still step 2. I'm going to multiply both sides by 2, so I get 2x equals 5 minus 3y. I'm going to subtract 5 and divide by negative 3. So if I subtract 5, I get 2x minus 5 and divide by a negative 3. That becomes a positive. And here is our inverse. Step 3 is to replace y with f inverse. So the inverse function of f is negative 2x over 3 plus 5/3. Okay, awesome. That's how you find an inverse. That's a linear function. Let's look at a cubic now for g of x. So step 1, replace g of x in this case with y. That'll be x cubed minus 4. Step 2, swap the x and the y, as well as solve. So we're going to add 4. That'll be y cubed. And then I'm going to do the inverse operation of y cubed, which is the cube root of x plus 4. Step 3, I'm going to write it in inverse notation. It's g of x. G inverse of x should equal the cube root of x plus 4. Okay, now the third one I've said to be careful. Okay, and I'll expose why in just a minute. But I'm going to take and do all the steps as I did in the previous two. Step 1, y equals the square root of 2x minus 3. Excuse the 1/2 power notation. Again, my computer is being funky. Okay, I'm going to swap x and y. So that would be the square root of 2y minus 3. Now I'm going to solve for y. I'm going to square x. I'm going to add 3. And then I'm going to divide by 2. That should be y. Okay, now I'm going to write this in inverse notation. X squared plus 3 over 2. Now, graphically, for number 1, the original function was a line, which would pass both the vertical and horizontal line test. So the inverse would also be a line and would pass both the vertical and horizontal line test. Okay, number 2, this is a cubic, which would, in this case, pass the vertical and horizontal line test. It's going to look kind of like this. Okay, here's -4. This is the point 0, -4. Therefore, that would pass the horizontal line test. Therefore, its inverse would pass the vertical line test. Okay, it would kind of look like this. Not perfect, but it's a decent sketch. This would be G inverse. Okay, now with number 3, this is going to be kind of interesting. The original, let me rewrite it in a separate form. Actually, this will be okay. I'm going to take the parent function square root of x. I'm going to shift it right 3 units. And then horizontally, I'm going to shrink it. Okay, right 3 units and then horizontally shrink it. So what I would end up with is if I horizontally shrink it by a factor of 1/2, the shift right 3 units would become 3/2, and then the square root would look kind of like this, right? Generally speaking. So I'm expecting the inverse to look like this to some extent. That was really poor, at least that's better, okay? But what's the problem with the inverse here? Well, the inverse here would also include that half of the function, which clearly does not map onto its inverse, which was h of x. Therefore, I have to set a specific restriction on this to be x is greater than or equal to 0. Right, that greater than or equal to 0, I really should have this in blue because that's how it's sketched. That greater than or equal to 0 isolates just this right half of that function. Okay, so you want to be careful and make sure and make that restriction on the domain. Okay, there aren't many of these that'll come up, but just beware. And most of the time they have to do with square roots and with quadratics. So let's move on to the last slide and do a little bit of algebra work and evaluation using inverse functions. Okay, so I've got a graph of f of x and g of x. And what I want to do is I'd like to evaluate each of the 5 of these. I think it would be really good practice for maybe I'll do the first 2 and then you try the last 3 on your own, and then we can look at your answers and you can check along with the video. So I'll do all the work as well, but I'd suggest pausing and attempting these. Okay, so f inverse of 0. Okay, I don't know what this value is going to be, right? But I do know that f of that value should equal 0. Okay, so as I look at f of x, which value gives me an output of 0? Well, I'm going to guess. I don't know exactly what this point is probably, I don't know, let's say 1/2 comma 0. So if f of 1/2 equals 0, then f inverse of 0 should equal 1/2. Okay. All right, now let's work on a composition. Let's work on the inside first. Let's talk about g of 2. So what is g of 2? Okay, g of 2 looks to be, I don't know, it's this point here. Let's call that 3. Okay, g of 2 is 3. Okay, and there's no inverses involved here, so we don't have to do a whole lot. What is f of 3? F of 3 looks to be -2, this point right here. Okay, so it looks like I would get a -2 here. All right, g of 0. G of 0 is 2 on the next one. So if g of 0 equals 2, then f inverse of 2, this is asking us for the, oops, I could put it here, I suppose. This would be equal to f inverse of 2. How would f inverse of 2 be related to f? Well, if I want to know what f inverse of 2 is, I want to know f of what gives me 2. Okay, so as I look at f, it looks like the only output that would be equal to 2 would be here. Therefore, 0, 2 would be our solution there. Therefore, f of 0 is 2. Thus, f inverse of 2 equals 0. Therefore, f inverse of g of 0 equals 0. This is some funky stuff, guys. Okay, f inverse of 2. F inverse of 2. Well, we actually just figured that out. That's 0. Okay, if f inverse of 2 is 0, then g of 0 would be equal to 2. Okay, the last one. G inverse of -2, we don't know what that equals, so we want to find g of what such that the output is -2. So g of, looks like -3 gives us an output of -2. So this would be -3, so this would be -3. So g inverse of -2 is -3. So this would be equal to the f inverse of -3. Let's relate f inverse of -3. Don't know what it equals, but I know that f of that number should equal -3. Let's see if f ever equals -3. Boy, there's a couple of options here. And here's why I say that. This value is -3, so I would say that's probably 1, -3. And there's also another value that's -3. So that could be 3.5, -3. So you could argue that f inverse of -3 has two values. Therefore, I could say that this would either be 1 or it could also be 3.5. So that's a very interesting one. But f inverse of g inverse of 2 could either be 1 or 3.5. Okay, guys, that's it on inverses. Again, shoot me a question. Make sure you do your push-ups, and we'll see you in the next video.